Hi, I'm Zhenyu. I'm glad to present our work Synergies between Affordance and Geometry, 6-soft graph detection via implicit representations. In this paper, we study the problem of 6-soft robotic grasping in dense clutter. It's an important part of robotic manipulation and has many applications including bin picking, part assembly, and logistics. In this problem, we are given a partial observation of a clutter of objects, and we need to predict a 6-soft grasp pose which can grasp one object and move it out of the clutter. Robotic grasping is a long-studied problem. Pioneer work solved the problem with geometric analysis. These methods give analytical solutions, but they usually require a full 3D model to compute geometric properties, which are not available in real world. Recent trends are end-to-end grasp learning with deep neural networks. These methods show high grasp performance, but they do not include explicit geometry reasoning. As a result, they often have limited generalization beyond training data. There are also some works that combine geometry reasoning and grasp prediction. They first reconstruct the 3D shape and then predict the grasp. These methods can operate on raw visual observations, but the grasp performance is subject to the 3D reconstruction quality, and 3D reconstruction itself is a difficult problem. Inspired by previous works, we believe the underlying reasoning in grasp affordance prediction and geometry understanding are not isolated. By grasp affordance, we mean likelihood of grasp success and grasp parameters. There are synergies between affordance and geometry reasoning. For example, when we want to grasp this mark given this observation, we know the graspable region is near the handle, so we would reconstruct the handle in our mind, and based on the reconstruction, we can predict how to grasp this mark in detail. In this paper, we exploit the synergies between affordance and geometry and propose to jointly learn grasp prediction and 3D reconstruction. The first thing we need to do is to find a unified representation for grasp affordance and 3D geometry. Inspired by recent progress in 3D vision community, we use implicit neural representations. Implicit neural representations are neural networks that map from 3D coordinates to quantities at the points. The quantities can be occupancy, sign distance function, and so on. Implicit neural representations are continuous and differentiable and can adaptively allocate computation. Then let me introduce the detailed architecture for method GIGA. First, we encode the input observation into a structured feature grid. The feature representation is shared for affordance and geometry reasoning. For affordance prediction, given a grasp center, we query the local feature at that point. After passing the local feature and grasp center into the learned affordance implicit function, we predict the grasp quality, orientation, and gripper width. It is a similar process in geometry prediction. We predict occupancy probability at a random query point. We collect our training data in a self-supervised way using Pi-Bullet simulator, and we set up two scenes, packed and pile. In the simulated experiment, we compare our method GIGA with two baselines. The first one is VGN, the sort of grasping in dense clutter. The other one, GIGA-F, is an ablative version of our method where geometry learning branch is removed. Since we are learning a continuous affordance function in GIGA, we can query at a higher resolution than VGN. We denote these results as GIGA HR. We evaluate the grasp success rate and declutter rate of all methods. Both metrics are better when they're higher. GIGA is better than GIGA-F. It indicates geometry learning facilitates affordance learning. GIGA HR is further better than GIGA, which indicates the continuity of implicit neural representation enables higher precision. We also visualize the learned grasp affordance and predictions. GIGA is able to predict more accurate and diverse grasps, especially in occluded regions. In real robot experiments, GIGA first grasps the small object behind because grasping it is unlikely to induce collisions, and gradually declutters the scene. Meanwhile, VGN gives up after 2 consecutive failures. We further visualize the 3D reconstruction results. We compare GIGA with GIGA-Geo, which discards the affordance learning branch and only learns 3D reconstruction. The reconstruction of GIGA focuses more on graspable parts of objects like the handles. In summary, we validate that the synergies between affordance and geometry can help improve grasp prediction, especially in occluded regions, and these synergies also drive the reconstruction to focus more on action-relevant parts. We also show that implicit neural representations serve as continuous and compact representations for both affordance and geometry. With structured feature grids and local implicit functions in GIGA, we can combine voxel grids with neural implicit functions. Our codes and pre-trained models are available on this website. Please feel free to try them out.